The following program is brought to you by Caltech.
Good evening. I'd like to welcome you to tonight's talk. I know you're going to enjoy it. Before I introduce our speaker tonight, I'd like to draw your attention to the next talk in the series. It's going to be held on December 7th, and the title of it is Design by Evolution, Engineering, Biology in the 21st Century, and it'll be presented by Professor Francis Arnold. So if you put that on your calendars, I'm sure you'll enjoy that talk coming up. It's my pleasure tonight to introduce to you our speaker for the Watson Lecture Series. He's been lecturing me for 7 years, so I know he's good at it. And he's been an integral part of these two missions that you're going to be hearing about tonight. He's been involved in space science for many, many years. He received his bachelor's degree in physics from Calvin College, and then later his master's degree in aerospace engineering from the University of Michigan in 1969. So he's been at this for a while. He spent over 40 years in solar system exploration, and his work at the Jet Propulsion Laboratory has involved work on missions such as Mariner 10, the Viking Orbiter, Galileo, Cassini, Deep Impact, and Stardust Next. He is a principal engineer on staff at the Instrument Systems Implementation and Concept section at the Jet Propulsion Laboratory. And his responsibilities over the years have included imaging system calibration, experiment planning, and mission operations. He's done science system engineering for advanced studies of the Europa Orbiter, Pluto Flyby, Solar Probe, and GEMO missions, and has served as the instrument lead on the JPL Advanced Concepts Development Team. He's published over 70 papers on global properties of various planets, satellites, asteroids, and comets, and on spacecraft imaging instruments and experiments. For all of his work, he's received a great deal of honor. He's been the recipient of numerous NASA Group Achievement Awards. He has also been a 3-time recipient of the NASA Exceptional Achievement Medal, which is a very high honor bestowed to very few people each year. And on top of that, he's also received the NASA Exceptional Service Medal. And in addition to that, asteroid 16958 has been named Clausen after his contributions to cometary science. So I'd like you to give Ken a warm welcome tonight, and I know that you're going to enjoy his talk.
Well, thank you very much for that kind introduction, Tim, and thank you all for coming. We're here to talk about comets tonight, why they're interesting, what they're made of, why we want to study them, what we've learned from sending spacecraft to visit comets, how the most recent comet spacecraft missions came about, what these missions plan to do and what the results were, and how the cost of these missions compared to those of other planetary spacecraft missions, and why they could be done so cheaply. So first, why are comets interesting? Well, for one thing, comets are beautiful. As these images show, these are some ground-based images of some representative comets, and comets have fascinated mankind for thousands of years as people observed their unexpected appearances and brief unveilings in the night sky. Here we see some sketches of comets produced in China about 300 BC. And the Chinese records of comet sightings stretch back as far as 1500 BC. This 17th century woodcut illustrates some natural disasters presumably caused by a 4th century comet. In times past, people thought comets were harbingers of all kinds of calamities on Earth. And maybe most famously, Halley's Comet, which was the first comet to be recognized as periodically returning every 76 years. Edmund Halley in 1705 used the laws of motion recently developed by Sir Isaac Newton to determine that several previously recorded comet observations were actually the same comet reappearing. And he correctly predicted its next appearance in 1758, proving that comets did reappear. And Halley has had its appearances then traced all the way back as far as 373 BC. Its most recent appearance was in 1986, and some of you may have had a chance to actually see Halley when it came by in 1986. The brightest comet ever recorded is Comet McNaught. It was seen in the year 2007, but it was only visible from the southern hemisphere of Earth, and so most of us wouldn't have had an opportunity to see it. And many other spectacular comet images have been captured using large ground-based telescopes. I think one of the most interesting is this one up here, where we can actually see a comet breaking apart as it neared the sun. And that happens on occasion. There's a small percentage of comets that don't survive their passage of the sun and just disintegrate and evaporate and are not seen again. So what are comets? What are these strange objects? Some people confuse comets with meteors or shooting stars, but they're not the same thing. Shooting stars are just pieces of space debris that enter the Earth's atmosphere and burn up in a matter of a few seconds, whereas comets are objects that travel through the solar system, usually a great distance from Earth, and they will remain visible for days to weeks at a time. We know that from observations on the ground that comets are composed of ice, dust, and gas, and they consist of four main parts. The core of a comet is the nucleus. It's made mostly of water ice and dirt, and it is typically only a few kilometers in size. And they're very dark, leading to their description as dirty snowballs or icy dirt balls. The coma is this halo of dust and gas that envelops the nucleus as it approaches the sun, and the sun warms the nucleus, and some of the ice is evaporated or sublimed off the nucleus and carries dust with it, and the coma can stretch out to several thousand kilometers from the nucleus. The dust tail is the most prominent feature of a comet. It's a trail of solid particles that are released from the nucleus and pushed away from it by the pressure of sunlight, and they can stretch for millions of miles away from the nucleus. And this is the feature that we can see as naked eye observers from Earth. And finally, there's often an ion tail, which is a stream of ionized gases that's pushed away from the nucleus by the solar wind. A couple other interesting facts about comet anatomy. When we look at the dust tail, the size of the particles in that tail are about the size of the particles in cigarette smoke. They're very fine particles. And the nucleus is basically inert unless until the time comes when it passes close to the sun and it warms up, and that's when it generates the coma and tail. And as it moves away from the sun again, it becomes inactive and is just an icy dirt ball again. If you want some more information on comets, I have some handouts on the stage here, and after the talk, you're welcome to come up and pick those up if you'd like. Well, where do comets come from? Comets are thought to originate from one of two huge reservoirs of objects that are far from the sun, far out in the solar system. The first reservoir is called the Kuiper Belt, and it's located out beyond the orbit of Pluto. and is a disk that lies close to the plane of the orbits of the rest of the planets. And the second reservoir is much further from the sun yet. It's called the Oort cloud, and it's more of a spherical distribution of objects. And we believe that there are billions of cometary objects in these reservoirs, but they're so far from the sun and the Earth typically that we really can't observe them directly. The way we observe comets and know where they come from is by looking at their orbits. Every so often, the orbit of one of those bodies out in the Kuiper belt or Oort cloud gets perturbed by the gravitational pull of Jupiter or a passing star, and it causes the object to come in to the inner part of the solar system, where it can become active by solar heating, and we can observe it and study it. Some comets have their orbits perturbed in a way that they come in and are captured in a fairly small orbit, one that goes out maybe as far as the planet Jupiter, and stays in that orbit. It typically has a period of 5 or 6 years, and those are called Jupiter family comets. There's another class of orbits which is like Comet Halley, which has a much longer orbital period. Halley is 76 years, so these are typically 50 to 100-year orbits, and they extend out at their most distant point much further from the sun. And finally, there are even more elongated orbits that last 50 to 100 years, and many times those comets will only pass close to the sun one time, and as they're at these great distances from the sun, their orbit will get perturbed again, and they won't come back into the inner solar system again. Well, why is it important to study comets? Planetary scientists are very interested in studying comets because they provide clues to the origin, the composition, and the evolution of our solar system, and presumably of other planetary systems about other stars. There's no reason to believe that the planetary systems, and we're discovering more all the time about other stars, wouldn't also have cometary reservoirs about them. Comets are thought to have formed at the beginning of our solar system, some 4.6 billion years ago, and they capture within them the raw materials from which the solar system was being formed. And so our ability to understand what the solar system was originally made of, there are clues in the comets that will help us understand that. The comets, as they reside so far from the sun and are kept frozen, their materials remain pristine. They're the same as they were billions of years ago. They don't change like the materials that actually coalesced to form the planets, which because of the high pressure and the heat of planet formation caused those materials to be changed, and so they don't represent the original building blocks any longer. So that's one reason we really want to understand comets. Second is that comets provide a source of water and organics to Earth. During the early history of the solar system, comet impacts on the forming Earth were more frequent than today, bringing in their materials and incorporating them into our own planet. And then finally, we need to recognize that within the Earth's geologic and biologic history, there have been comet impacts, and they've had big effects on Earth. An example is the impact at the Cretaceous-Tertiary boundary that caused the extinction of the dinosaurs. That was thought to be a comet or an asteroid impact causing that. So that kind of an event, of course, is a very rare occurrence. It's not one that's going to happen probably in our lifetime. They only happen every 100 million years or so, but it's an event that would have very high consequences. And so we don't want to become complacent about that possibility either. Okay, why do we need spacecraft to study comets? Can't we learn enough just from ground-based observations? And well, we have learned a lot from Earth observers, but only a spacecraft can get close enough to actually study the nucleus at the heart of every comet. And it's the nucleus that produces the rest of the coma and tail that we can see from Earth. So we really need to get up close in order to understand the nucleus. And it's the nucleus that would ever be a threat if a comet ever hit Earth. The tail is not a threat. That's so diffuse, it's not a problem. In fact, the Earth passes through cometary debris clouds every year. And we see those as meteor showers. Those occur when the Earth passes through leftover debris from previous comets. And if you're interested in observing that, you can go out in a few weeks to the mountains or the deserts and watch the Leonid meteor shower. What we would really like to do is get a sample of a comet, to land on it and bring a piece back to Earth. And that would really help us to understand what the nucleus is made of and what its structure is better. And this will help us understand whether there are methods that we can use to protect the Earth. If a comet should be discovered that's on an impact course with Earth, what can we do to deflect it so we can avoid that threat? Well, let's look at previous spacecraft missions to comets. Prior to a year ago, there were 4 comets that had been visited by close spacecraft flybys. The first was Comet Halley, which was visited in 1986 when it came back by a European Giotto spacecraft and a Russian Vega spacecraft. The US defaulted. We didn't send a spacecraft to Halley when it came through. The first US encounter was with the Deep Space One spacecraft, which flew by Comet Borrelly. And then Stardust spacecraft flew by Comet Wild 2, and the Deep Impact spacecraft flew by Comet Tempel 1. So those are the 4 that we saw prior to a year ago. And this is a montage of some of the best images of those 4 comets, nuclei, seen in the correct relative size one to another. And if you notice, the sizes they're pretty small. They're 5 to 10 kilometer diameter objects, so not real big. Okay, these missions provided us some new insight into the surface characteristics of cometary nuclei, but we still have a lot of questions. It seems like every mission raises as many questions as it answers. So we still have questions about how strong a nucleus is, how dense is it, what's its internal structure, can you push it around, can you blow it up? We don't know. We don't know exactly how the nucleus evolves and releases its gases during each perihelion passage yet. So there are plenty of reasons to study comets further. What elements are inside the nucleus? How does the inside differ from the outside? And will we ever be able to alter a comet's trajectory? Well, in the past year, NASA has completed the next 2 missions in cometary exploration. So I just want to review for you a little bit about how those missions came about, because they're kind of unique. Each of these missions used spacecraft that were already flying and had successfully completed their original mission. But the spacecraft remained healthy and had adequate fuel remaining to allow them to be used to extend the scientific studies that could be done. And these were the Deep Impact and the Stardust spacecraft, the last 2 that had visited comets prior to a year ago. So NASA recognized that this was a good opportunity to use these spacecraft, and that using them to do another mission held the promise of being low risk and low cost means to maximize the scientific gains from these spacecraft. So the spacecraft, when they completed their original mission, were put into a sleep mode, kind of hibernating, waiting for the evaluation of proposals to do a follow-on mission. And the scientific community submitted proposals to NASA as a part of its Discovery program in 2006. And there were two proposals that were selected by NASA to use the Deep Impact spacecraft. One is the Deep Impact Extended Investigation, which in good NASA practice, we always give acronyms to everything, so it's called DIXI. And the second one is the Extrasolar Planet Observation and Characterization mission called EPOC. And NASA said, well, we can do both these proposals. So we're going to combine them into one mission, and so they combined EPOC and DIXI into epoxy. Tonight I'm only going to discuss DIXI because we're doing comets tonight. The EPOC looked at planets around other stars. As far as the Stardust spacecraft was concerned, there was one proposal that NASA selected, and that was a mission called Stardust Next, or the New Exploration of Tempel, because that mission was to go back to the comet Tempel 1, the same one that Deep Impact had visited in 2005. Well, it might seem like, well, this is an obvious thing to do. Let's use a spacecraft that's up there and flying already to do some more good things. But it's not as straightforward or simple as that to just reuse another spacecraft to do a different mission. There are a lot of challenges and things that you have to think about and worry about. You have to know that there's enough fuel to accomplish all the trajectory maneuvers and to maintain the spacecraft attitude control until you get to your new target. Will the solar arrays generate enough power? Will all the equipment last long enough to complete the new mission? Have there already been some equipment failures, possibly? Is the telecommunication system powerful enough to return all the necessary data to Earth? And are the instruments well suited to study the object you're going to go to? They were designed for the first mission. How well will they do science at the second target? And is the science they can do worth the extra cost? So to answer the last question, is it worth the cost? You need to look at what is the scientific rationale for the mission. For DIXI, the main thrust of the mission, the main science goal was to better understand the diversity of comets. We picked as our target a comet called Hartley 2, which we knew was much smaller than any of the other comet nuclei that we had visited. And yet, it was much more active. It released much more dust and gas than, for example, Tempel 1 did. So it was a very different type of comet. And by studying those differences, we can learn more about the sources of the cometary activities, the depth of the ice in the comet, and the physics of how comets work. And that will help us understand not only the comets, but the origin of the solar system. And the advantage of doing that with a spacecraft that had visited a different comet, it has the same instruments. And so you don't have confusion about, am I seeing an instrumental effect or a real cometary effect, because the instrumentation is the same. Stardust Next, on the other hand, gave us a unique opportunity to observe changes in a comet nucleus that occurred as a result of one perihelion passage close to the Sun, which occurred in between the Deep Impact encounter and the planned Stardust Next encounter, which was going to happen 5.5 years later. And so it gave us a chance then to see how much that surface had changed. It also gave us a chance to hopefully see the crater that was created by the deep impact impactor that hit Temple 1 in 2005. With the impact created so much dust coming off the comet that we were never able to see through down to the surface and see the crater that was made. So we were very interested in going back and see what that crater looked like if we could. And then we also wanted to see the rest of the nucleus. When you do a very fast flyby like we do of these comets, you only see the half that's illuminated by the sun at that time. And so we hope to be able to extend our coverage of the nucleus by observing it a second time. So I'm going to go through what our plans were for each of these two missions and then present some of the results. And I'll talk about epoxy first. The epoxy mission flew by Hartley 2 almost exactly a year ago. It was November 4 of last year that the closest approach to Hartley took place. And as I mentioned, it used the Deep Impact spacecraft, which had completed its flyby of Temple 1 on July 4, 2005. And the leader of the the Dixie mission, the epoxy mission, was Dr. Michael Ahern from the University of Maryland, who's shown here. Okay, this is the Deep Impact spacecraft before launch. This is the impactor that was released and that hit Temple 1. And so when Dixie took it over, the impactor was no more. It was destroyed by impacting, and so we put that to bed and operated with the instruments that were on the rest of the spacecraft, the flyby spacecraft, these big telescopes here, which supported 2 cameras and a near-infrared spectrometer. This is a picture of the impact that occurred in 2005, and you can see the tremendous release of material that was exploded out of the comet when the impactor hit. And down under there someplace is the crater we couldn't see. So this is just a little video clip, a video clip about the mission and the trajectory. And you can see the spacecraft orbiting around the sun. It flew by Temple 1. We went around the sun several more times before we ended up encountering Hartley 2 last year. And this is a still plot that shows the trajectory. And it took us 4 times flying close by the Earth and using the Earth's gravity to shape our trajectory and get it on the right course to intersect Hartley 2. This is a picture of Hartley 2 taken from the ground, showing its coma starting to grow as it came closer to Earth and the sun. And these are a couple more pictures. This one was taken from the Hubble Space Telescope. And this is another Earth-based view. This one was taken about 10 days before closest approach. And finally, here's another picture. This was taken by our spacecraft team chief, Steve Whistler, in his backyard in Sierra Madre. So the science goals for the Dixie mission, as I said, understand comet diversity, determine how unique the discoveries were at Temple 1 and how different Hartley 2 was going to be, understand the heterogeneity within cometary nuclei, and thereby constrain cometary formation and evolution theories. These were our measurement objectives. These are the things we really wanted to do when we encountered Hartley 2. We wanted to look for outbursts. We saw when we flew by Temple 1 with the Deep Impact spacecraft, we saw frequent outbursts of dust and gas coming off the nucleus, and we wanted to see if we would see the same thing at Hartley 2. We wanted to measure what gases were in the innermost part of the coma that can't be observed from Earth. We wanted to see if we would see volatile material on the surface, like patches of water ice that we could recognize, which we did see on Temple 1. So we wanted to see if we would see that again on Hartley 2. We wanted to determine the size of the nucleus, and we wanted to characterize the topographic features on the surface to understand the geology and the history of the nucleus, and finally measure the temperature of the surface and how that varied with the solar illumination. So Hartley 2, as I said, was much smaller than the nuclei that had been visited before. It's only about 600 meters in radius. And the nucleus is very dark. It's darker than a piece of charcoal you might put in your grill. It only reflects about 3% of the sunlight that falls upon it. And its orbital period is about 6.5 years. So these are some of the things we knew about Hartley before we got there. As I mentioned, Hartley is kind of in a class by itself. It's only about 1/5 the radius of Temple 1, but it shows about 10 times the gas activity and about 2 times the dust activity. And so in terms of the amount of material that's ejected relative to its size, Hartley is way out of bed with where the rest of the comets are that we have seen. So it looked like Hartley was emitting dust and gas from over 100% of its surface. How could that be? So that's what we really wanted to understand. We knew the rotation period of Hartley is about 17 hours. We got that from Earth-based observations. This is a plot of the brightness of the bare nucleus when it was far from the sun as a function of its rotational phase, and you can see its brightness periodically changing as it spins. And the fact that we had these peaks and valleys allowed us to determine that it was an elongated nucleus with a long axis at least 2 times longer than the short axis. So we knew a little bit of what to expect about the shape and the rotation of Hartley before we got there. Well, our plan from the spacecraft was to observe Hartley with all the 3 instruments, starting about a month before we got to closest approach and lasting about 3 weeks after closest approach. Closest approach was planned to be 700 kilometers from the nucleus, and the nucleus was going to be about half lit by the sun from our point of view, from our perspective. These encounters happened very fast. The flyby speed was 12.3 kilometers per second, and so there was only about 3 hours of time during which the nucleus would be more than just a point source as viewed by our cameras. So we had only a short amount of time to really study the nucleus up close. We had planned a sequence that was going to return about 120,000 images and spectra during those 7 weeks around the closest approach period. This video gives you an idea of what the spacecraft flyby of the nucleus looked like, what its geometry was. And you can see we go by very quickly and then we're on our way again. This chart shows a little bit more about the geometry. You can see we flew by, and as the spacecraft flies by, we rotate the spacecraft so that the instruments remain pointed at the comet throughout the entire encounter, and the solar panels are kept oriented toward the sun line so we maintain power throughout the encounter. Stardust Next, I'll talk about the plans for Stardust Next. Its encounter was on Valentine's Day this year, February 14. We tend to have encounters happen on holidays for some unknown reason.
I'm Tim Larson, Stardust Next project manager. The Stardust spacecraft was launched in 1999 from Cape Canaveral.
We have main engine start, 0 and liftoff.
And began its journey around the sun and the solar system. On the way to its primary objective, Cometville 2, it had the opportunity to fly by an asteroid called Anne Frank and take some images of that asteroid as it flew by. Then it continued orbiting the sun, getting closer and closer to Ville 2, taking images of the comet as it approached and then departed. And at the same time, it had a sample collection capsule open, collecting dust samples from that comet, and that was returned to Earth in January of 2006. Those samples are still being analyzed today and yielding very interesting results. The Stardust spacecraft continued orbiting the sun, and we've now been able to retarget that spacecraft to take it near another comet, Tempel 1. Its closest approach to Tempel 1 will occur on February 14, 2011, approximately 8:30 in the evening Pacific time. The spacecraft will fly by 200 kilometers from the nucleus of this comet and will take 72 images of the comet that it'll store in its onboard memory. And it'll point the high-gain antenna back at Earth and replay all those images to the ground over the next 12 or 13 hours. After the images are safely received on the ground, it will continue taking outbound images of this comet for a few weeks until the fuel tanks will be almost empty, and at that point the spacecraft will essentially be retired after long duty and 2 very successful missions for NASA.
That was Tim Larson who introduced me tonight, who's our project manager for both these missions that was narrating that clip. So this is Tempel 1, our target for Stardust Next, and the question was, how much has it changed since this picture was taken by Deep Impact? So our mission objectives, primary one is to look for changes between successive perihelion passages of a cometary nucleus, the same nucleus. We wanted to extend the geologic mapping to the parts of the nucleus we hadn't seen before. Particularly, we were interested in looking for layering, which we had seen. On one side of Tempel 1, we wanted to know how ubiquitous that was. We also were interested in looking for smooth flow deposits, active areas, exposures of water ice on the new territory. And then we wanted to, if possible, look at the crater formed by Deep Impact. This is a sketch of the computer drawing of the Stardust spacecraft. It shows the science instruments. This is a camera mounted here. We had a dust flux monitor instrument mounted on the front of the spacecraft in the direction of flight. And then there was another dust instrument, a dust composition measurement instrument that was mounted on the side of the spacecraft we can't see here. So those were our 3 instruments on Stardust Next. Well, we had a lot of challenges with this spacecraft. It was getting old. We had already had to switch to our backup computer hardware. We were encountering continual contamination of the camera. That had to be baked away by heating the instrument repeatedly. It would clean it up for a while, and then the contamination would come back. We had to keep doing that. Our attitude control system was such that every time we changed the attitude of the spacecraft, it also imparted a little bit of change in velocity in a direction that made navigation difficult because it would affect the trajectory. There was a big question about what side of the comet we would actually see when we got there, because the comet was rotating, and how predictable would that rotation be? And we knew we were constrained on how much fuel we had available, and there was quite a bit of uncertainty in how much we actually had. We also had some questions about how early we would be able to detect the comet in our camera. We needed to use the camera to navigate the spacecraft to our close flyby point, and we wanted to fly by as close as we could in order to maximize the science, but we needed good navigation to be able to do that. So perhaps the biggest challenge was the arrival time challenge. We needed to To accomplish our science objectives, we needed to arrive when the nucleus was oriented relative to the sun in the right way and relative to our trajectory in the right way in order to see both areas that deep impact saw to look for changes, to try to see new areas that deep impact couldn't see, and also to try to see the comet, the crater in its location. However, we knew from previous observations that the spin period of Tempel 1 varied. And each time it went through an orbit and went close to the sun, its spin period changed somewhat. And so it was difficult to predict exactly how that nucleus was going to be oriented at the time we got there. And the other problem was that in order to adjust our arrival time so that the comet was oriented the way we wanted it to be, we had to make that adjustment a year before we got there, because that was when it was most efficient to do it from a trajectory point of view and a fuel point of view. So we had a challenge of making that prediction a year in advance. This is a plot of the spin rate of Tempel 1, a historical plot through the years over 1999 to 2011. Each perihelion time is marked by these vertical dashed lines, and so you can see that the spin period changes as we fly by the sun each time, and the gases that are emitted affect the spinning of the nucleus. So we had observed that happen twice. Our encounter was going to be 34 days after this perihelion, so we had to predict what was going to happen here, and we had to do that a year before it happened. So that was our challenge. In order to meet that challenge, there was a huge effort made. We recruited observers from all around the world and all the largest telescopes in the world to monitor the spin of Tempel 1 and to support our modeling of how that spin was going to vary. Through those telescopes, we gathered this light curve data, again, when the nucleus was far from the sun, very dim, and we looked at what its spin period was by looking at this periodic change in brightness. And that's what helped us predict the spin state of the nucleus when we got there. As I said, we had to commit a year in advance, and based on our best modeling at that time, we elected to delay our arrival time by 8.5 hours, which was about 1/5 of a nucleus rotation. And that was about the maximum amount of fuel. That adjustment required the maximum amount of fuel that we felt we could afford to spend to make that adjustment and still have enough left to complete the rest of the mission. So only time was going to tell whether we got it right or not. There was a lot of people that were somewhat doubtful. So those were our plans. Let's see the results. We'll go back to the epoxy mission first. We began observing Hartley 2 months before encounter with the imaging, and about 5 weeks before encounter with the spectrometer, monitoring the nucleus rotation and looking for gas and dust outbursts. These are a couple of the first pictures that we took from the spacecraft. This is, I think, one of the very first ones. This is the comet here. All these are background stars that we saw in our cameras. And then as we got closer, here's a view as the coma is growing. This is a video clip of the coma growing and brightening and dimming as the nucleus rotates. This started about, I think it was 2 weeks before encounter. The rotation period is 40 hours for this nucleus. And so we see the periodic brightening and dimming of the coma as the nucleus rotates every 40 hours. And as the spacecraft gets closer, the whole thing brightens up. And you can see that happening here. The little red X is where the center of the nucleus is. That's an artifact we put on just to give you a reference. So using that kind of data, we generated these light curves and used that to determine the rotation period for Hartley 2. And from that, we determined that Hartley 2 was rotating in what we call an excited state. That is, it's spinning about 2 axes at the same time, not just one. So it's kind of like a wobbly football spiral pass. It's rotating around both a short axis and a long axis. And in addition, we noticed that the rotation period was changing as we went through the encounter period as a result of the jetting action of the gas emissions that apply torques to the nucleus and change its spin period. About one axis, the spin rate was increasing, and about the other axis, it was decreasing. This chart shows the period changing as a function of time relative to encounter. Far before encounter, from Earth-based observations, we had this period, and when we started measuring, we got the same period, and as we went closer and closer, we saw that period changing. This is the period about the short axis, I believe. So you can see the effect of the jetting action of the released material on the spin state of the nucleus. But the nucleus is what we're really interested in, and so this is what the nucleus looked like close up when we flew by. That was kind of fast, so I'll slow it down a little bit, and you can get a better view of the perspective of the nucleus as our spacecraft flew by. So it was amazing. When we first saw these pictures, it was amazing because Hartley 2 looked different than anything we had seen before. And very interesting, had kind of a bowling pin shape or a peanut shape or a dog bone, people called it. These 2 lobes on each end and a smooth waist in the middle. We saw lots of dust and gas emission from the lobes, but none from the middle. And the lobes are kind of rough, and the middle is very smooth. So these are just 5 of our close-up pictures with different perspectives showing Hartley 2. And just to give you an impression of the size of this thing, it's here superimposed to scale over a familiar national landmark. If anybody recognizes this landmark, that's the National Mall in Washington. There's the Washington Monument and the Capitol building. So if you've visited there, you get an idea of how big this thing is. Okay, we saw lots of jetting activity at Hartley, which was kind of what we expected. We knew it was a very active comet. And using our infrared spectrometer, we were able to tell what some of the materials were that were coming off the comet. We had a lot of water vapor that we measured, and it was more concentrated over this waist area. We also measured water ice, and that was concentrated more off the small lobe on the sunward side. The same with organics and carbon dioxide. So we were able to detect and see the distribution of those materials within the inner coma using the infrared spectrometer. Now you might say, well, how do you know what you're looking at? A spectrometer measures the brightness of an object as it depends on different wavelengths of light. And our spectrometer measures light in the 1 to 5 micron bandpass, which is the near infrared band, shortwave infrared. It's beyond what our eye can see. And this is the brightness of a place in the nucleus that we measured in Hartley 2's nucleus versus wavelength. And we know that different materials emit light at specific wavelengths. So we knew that from laboratory measurements that water vapor emits here at about 2.7 microns, carbon dioxide out here at about 4.3 microns, and various organic materials emit at about 3.3 microns. So using that information, we could tell what we were looking at. We also can tell for the water ice what size particles we're observing. This again is the measurement we made of Hartley 2, and it's compared to a measurement of water ice particles of different sizes. 100 micron size particles, 10 micron size particles, and 1 micron size particles. So if you shift these to try to overlay them, I think you can see that the 1 micron size particles match the best. You just ignore this peak here, which is the water vapor peak, and match the ice spectrum. And so we knew that the size of the particles was very small, like a micron in size. So there's very interesting science that can be done with that instrument. Okay, I'm going to show you a clip of a press conference that shows some of the results of our...
We flew by it at a speed of about 27,000 miles per hour, and the spacecraft was slightly below the comet in the sunplane.
Who would have thought that we actually get to see a comet close up like we just did? And when we first saw this, our mouths just dropped. Our whole team just dropped. Because we can begin to see, if you look very close to the nucleus, you can see things that are slowly moving, but then as you go farther away, they're really migrating. To me, this whole thing looks like a snow globe that you're just simply shaking and watching it fly.
When we saw the images come down, even in real time in the raw data, and realized we had a cloud of snow around the nucleus, we were astounded. Those are not stars, those are all chunks of ice. We think the biggest ones are at least the size of a golf ball and possibly up to the size of a basketball.
They're akin more to maybe a dandelion. So what that means is that the snowballs are not what we might have thought to begin with. We're not seeing softballs or even ice cubes. What we're seeing are fluffy aggregates of very small pieces of ice. While it's true that water is where the ice is, in fact it's everywhere, particularly on the sunward side of the image, to our great surprise, there's a tremendous enhancement of water vapor coming out of the waste of this body. We wouldn't expect this at all, and so what we're seeing is an indication that here the ice is still on the inside, it's being heated up by the sun, and that drives the water off.
We're still continuing to collect data. We've collected about 32,000 images of the comet since November 4th. We continue to look at it about every 2 minutes and acquire data, returning over 3,000 images a day of data. By the time we're all finished with this science mission, around Thanksgiving is our last imaging session, we will return about 120,000 images of the comet, and that represents about 22 gigabytes of data.
Okay, so that was one of the other exciting observations we made when we got to Hartley, is all these snowballs or these aggregates of water ice coming off the nucleus. And I'm just going to flip quickly through some of the close-up pictures that show the cosmic snowstorm, as we call it. And as was mentioned in the clip, we can actually trace the movement of particular particles from frame to frame and determine their trajectories. We determine that they're being pushed away from the nucleus by sunlight. And this really answered the question of how can Hartley be emitting material over more than 100% of its surface? Well, the fact is, it's emitting material from all these little snowballs. So it's not just the area of the nucleus itself, but you have to add in all the area of all these millions of snowballs, and that's how we get the added emission from Hartley. So that was a very interesting observation and answer to a question. Okay, so I think I'm going to move through this. We've heard most of this from the press conference. We learned about the snowstorm, and we learned about how Hartley can be what we call a hyperactive comet. We learned that the material is being driven off mostly by the release of carbon dioxide, and the water is coming off mostly from these snow chunks that are lifted up off the surface. And we easily can see the jets, and it looks like the central smooth waste is just redeposited material that has fallen back to the surface and accumulated there. So now we have 5 very different comets that we've observed, and you can see their relative sizes here. This is the relative size of Hartley 2, not the blow-up, this little one, compared to the others. So you can see how much smaller it is than the other comets. And so we're learning more about comets, but don't have all the answers yet. This is the legacy of the Deep Impact spacecraft observing Tempel 1 and Hartley 2. Okay, Stardust Next results. Recall we went back to Tempel 1, which had been impacted by Deep Impact, and we had a very successful encounter on Valentine's Day. Again, we flew by at 11 kilometers a second and collected our primary data set was the 72 images that we could store in the plus or minus 4 minutes around closest approach. The best resolution pictures were about 12 meters per pixel, and we also collected data from the 2 dust instruments. This is our first image where we detected Tempel 1 with our camera. We actually had to add, I think it was 8 frames together in order to get enough signal to see it. But this allowed us to begin our navigation to the comet flyby point. By about a week before closest approach, we were able to detect Tempel in a single frame. We didn't have to add images anymore. So this is a movie showing the 72 images that we acquired during our close flyby, and you can maybe, if you remember what Tempel 1 looked like from Deep Impact, you can recognize some of the features because this is the side that Deep Impact saw. So we saw that on our approach, and then as we went by the closest point, we started to see new territory, and then on the outbound portion, it was the side of the nucleus that Deep Impact did not see. So it turned out that our arrival time correction that we had to execute a year before was right on. We couldn't have asked for a better solution, and I give a lot of credit to the people who did that modeling and got us a good prediction of when we needed to arrive in order to see the things that we wanted to see. So these are just 4 still shots extracted from the 72, showing the different sides of Tempel 1. This is a view of the side seen by Deep Impact. And this is the Deep Impact view and the Stardust Next view, and these arrows connect the features that we saw in common between the two. So you can see that we were able to look for changes. But if you look at that, you probably don't see very many changes because we didn't see very many changes. What about the crater? Okay, well, these are images that were taken by the Deep Impact impactor on its way in. This nested set of frame outlines show the increasing resolution as the impactor headed toward the surface and impacted here in the middle of the circle. And this is a higher resolution view and one of the highest resolution views. So from these images, we knew pretty accurately where the impact occurred relative to these features. And if you look at the Deep Impact image and the Stardust image of that area, you can easily recognize common features, even though the resolution of the Stardust image is not nearly as good as the impactor view because the impactor got much closer. And the sun illumination is a little different, but you can still easily recognize the features. And This is about where we expected the impact crater to be. It's pretty hard to tell, but we use stereo imaging and a lot of staring, and we think we see a very faint outline of what might be the remnants of a crater. But it looks like it's very subdued, mostly covered up again, probably by material falling back into the crater or the crater walls collapsing. So that tells us something. It tells us that the surface of the comet is very weak and very porous. It doesn't hold a shape. It doesn't have enough strength to hold the shape of a crater like the craters on the moon. So even though we don't see a pronounced crater, we learned a lot about what the surface was like by observing. And then we saw new territory. This is the side Deep Impact did not see. And if you remember, we were looking for layering, and we saw terraced layers. We noticed these knobs that are shown in red. There were smooth flows with pits in them. So all the kinds of geology we were wondering about, we were able to see on the far side. We did not see any exposed ice patches, though. That was one of the things we were looking for and did not find. So how much did the comet change in 5 years? If you looked at the comparison pictures, you'd say not too much. We weren't sure we were even going to be able to recognize anything that we saw in Deep Impact, that it would have changed that much. But in fact, it changed very little. There are a few places where we do observe changes. This is a Deep Impact view and a Stardust view of the smooth flow feature. And we do see changes around the edge of the flow and in these pits, which seem to have coalesced into a larger area. But the changes are very minimal. And if you look at the end of that flow feature, you can see that this triangular feature is no longer there. So there are some places where material has disappeared as a result of the perihelion passage, but they're pretty minimal. We estimate that if the material loss were averaged over the whole surface, we would lose about 0.5 meter of material. That's how much we see coming off, but we see from these images that it's restricted to very localized areas and preferentially in the youngest deposits. The jetting was pretty weak. It's probably mostly because we encountered a month after perihelion. We did take data with the dust instruments. This is what it sounds like when the dust impacts the spacecraft. And you can see it's very bursty. The dust isn't evenly distributed throughout the coma, but we run into irregular places where there's dust. Okay, so we had a very successful encounter. The spin prediction was right on. We found a subdued crater at the impact site and noticed changes restricted to very localized areas. Saw new features and familiar features on the far side that hadn't been seen by Deep Impact. And we know that the surface texture is kind of like that of loose snow, and this would be a very nice target to go back to and land on and gather a sample, because there's smooth areas that look like it would be safe to land on. We had to decommission the spacecraft afterward. We did that by burning the remaining fuel as a test as to how much fuel we really had left on board. There were estimates that varied by from nearly 0 to about 4 kilometers. When we did the final burn, we discovered we had only 311 grams of fuel left, which is just over a cup. And so out of the 85 kilograms we started with, we really were running on fumes at the end. So how cheap were these missions? I said they were cheap. $43 million for epoxy, $29 million for NEXT. Well, to you and I, that doesn't sound like cheap, but if you compare that to a typical NASA, the lowest cost planetary mission that NASA does is a discovery mission, and they're about 500 million. And so the cost of these missions is less than 10% of the cost of a new mission. So this is a bargain in terms of planetary exploration. So I'm running out of time here. I'm going to go quickly through the conclusions. Every comet is different. Every comet surprises us. We've learned a lot, but there's a lot yet to learn. The next comet mission is to Churyumov-Gerasimenko. Say that a few times. It's a European mission called Rosetta. It will arrive in 2014, and it includes a lander. So we're hoping that will be successful, and we'll learn a lot from that lander. Deep Impact spacecraft is still flying. It's still healthy. The team is operating, and we're just waiting for NASA to decide what they want us to do. And NASA will eventually tell us what they want us to do, but hopefully we can do some more science with this spacecraft because it's in good shape. These are the people, some of the people that make a mission happen. It doesn't just happen without people. And they're the ones who deserve the credit for the new knowledge that these missions have provided to all of us. And I'll just close on a personal note. I love exploring space, and I'm excited by scientific discovery. But on the other hand, I don't look to science to answer the ultimate questions of life, questions of where we come from and why we're here and where we're going. Those are questions of faith, and it's my faith that motivates me in my career and in my personal life. So with that, I'll close, and I thank you very much for your attention.